Welcome to the DIY Honda Garage channel. This presentation will provide a comprehensive troubleshooting guide for DTC P16E3, which indicates a PGM-FI, programmed fuel injection battery sensor LIN communication error, specifically for the Honda CRV models from 2017 to 2022. DTC codes are diagnostic trouble codes that help identify issues within a vehicle's electronic systems. The specific error of P16E3 suggests a communication breakdown between the battery sensor and the vehicle's electronic control unit, ECU, raising concerns about battery management and overall vehicle operation. It is crucial to address this issue, as improper communication could lead to battery malfunctions, affecting the vehicle's performance and reliability. Understanding the components involved, performing methodical checks, and following the recommended troubleshooting steps are essential to diagnosing and resolving this error. DTC P16E3 indicates a PGM-FI-Battery sensor LIN communication error, which signifies a problem with the LIN, local interconnect network communication, specifically between the battery sensor and the vehicle's powertrain control module, PCM. The battery sensor is a critical component located near the vehicle's 12-volt battery. Its primary role is to monitor the battery's voltage and current, providing real-time data to the PCM to ensure optimal operation of the vehicle's electrical system. When communication is disrupted, the PCM may not receive accurate battery performance data, compromising the vehicle's functionality and potentially leading to battery-related issues. This error can be confirmed by the Honda Diagnostic System, HDS, which enables technicians to interface with the vehicle's systems for accurate diagnostics. Several factors could lead to the occurrence of DTC P16E3. One common cause is loose terminal connections at the 12-volt battery sensor, which may result in intermittent or missing signals. Such disconnections can prevent the proper functioning of the battery management system, leading to erroneous data reporting. Additionally, the LIN wires connecting the battery sensor to the PCM could experience shorts or opens, which would also hinder communication. Finally, a faulty battery sensor itself could be the root of the issue, leading to incorrect readings or no readings at all. Proper investigation of these components is crucial to accurately pinpointing the failure source. Drivers may notice various symptoms associated with DTC P16E3. Commonly, warning lights may illuminate on the dashboard, indicating that there is a battery management issue that requires attention. Additionally, the vehicle may exhibit battery performance problems, such as difficulty starting, reduced power availability, or other electrical malfunctions. Erratic behavior of electrical components, like headlights flickering or issues with power accessories, may also become apparent due to this LIN communication breakdown. Awareness of these symptoms can aid drivers in recognizing when to seek professional diagnosis and repair, improving the chances of resolving the underlying issue before it leads to more significant problems. The first step in troubleshooting DTC P16E3 involves verifying the problem through the Honda Diagnostic System, HDS. Begin by turning the vehicle to the on mode, which powers the vehicle's electronic systems without starting the engine. The next step is to clear the DTC using the HDS tool. Clearing these codes helps reset the PCM and allows for a fresh attempt at generating any potential errors. After clearing the codes, turn the vehicle to the off, lock mode and then return to on mode after a short interval. Wait for approximately 60 seconds before checking for any pending or confirmed DTCs again. Observing whether DTC P16E3 reappears provides valuable insight into whether the issue persists or if it may have been a temporary glitch. In the second step of troubleshooting, the next action is to perform a DTC check using the HDS once again. check for any pending or confirmed DTCs, which might suggest that multiple issues can exist concurrently within the system. If DTC P16E3 is indicated, you would then proceed to a step more specific to that code. Identifying other DTCs provides a broader understanding of potential systemic issues affecting the vehicle's performance. If no related DTCs are confirmed, the troubleshooting can continue to investigate other possibilities surrounding the potential voltage communication error that caused DTC P16E3 initially. Next, a DTC check is performed specifically for P16E8 using the HDS. This step involves checking if the system indicates a PGM-FI shutter grille LIN communication error, which if confirmed, would prompt further investigation into that code. If this code is present, technicians are instructed to follow the specific troubleshooting path related to DTC P16E8. However, if no issues are found, this indicates that the primary concern surrounding DTC P16E3 may not be directly linked to the shutter grille communication. This structured process of checking related DTC codes aids in thorough diagnostics and helps isolate the original problem more effectively. For the fourth troubleshooting step, check for the presence of DTC P16E5, which indicates a LIN communication error related to the PCM DC-DC converter. This error can coincide with the issues presented by P16E3, underscoring the importance of verifying each code meticulously. By utilizing the HDS for these checks, technicians can establish whether other components may be contributing to the communication error. Should DTC P16E5 appear, instructions will guide you through further specific diagnostics. Maintaining a clear pathway to explore interactions between these codes helps ensure that extensive communication failures can be identified and resolved effectively. In this troubleshooting step, you aim to determine the possible failure area related to the LIN communication. Begin by ensuring that the vehicle is turned to the off/lock mode. Disconnect the 12-volt battery sensor 2P connector and measure the resistance between the designated test points. The aim is to establish whether the resistance is 1 megaohm or more when the vehicle is in this state, which would suggest that the communication line is likely intact. If the resistance is insufficient, it indicates that either a short exists or the wiring is compromised, necessitating further investigations. This step is critical, as establishing the condition of the wiring helps guide subsequent troubleshooting actions. Step 6 necessitates performing detailed checks for shorted wires in the LIN communication. Begin by using the HDS to jump the SCS security control system line, followed by waiting for over 1 minute to ensure an accurate reading. After this, measure the continuity between the 12-volt battery sensor's 2P connector terminal and body ground, while disconnecting other connected components one at a time, like the alternator or PCM connector. If continuity is interrupted upon disconnecting one of these connectors, it implies that the LIN wiring is functioning correctly, guiding the technician on what to replace next. This meticulous method helps isolate the issue to particular components without hastily replacing parts. In this step, you'll focus on determining if the 12-volt battery sensor or related components are the source of the issue. Start by reconnecting the 12-volt battery sensor 2P connector. Then proceed to disconnect the alternator 1P connector for isolation. Measure the resistance between the corresponding test points. The target resistance here should also be equal to or greater than 1 megaohm for proper functionality. If the resistance is lower, it would indicate a defective battery sensor, leading to a recommendation for replacement. Through this method, technicians can efficiently narrow down potential failures related to the battery and its immediate components. During this step, another open wire check on the LIN communication line is necessary. Jump the SCS line again with the HDS, ensuring the vehicle is turned to off/lock mode. Disconnect both the 12-volt battery sensor and the PCM connector before proceeding to perform further resistance checks. This test aims to verify whether the resistance between specified test points is at or below 1.0 ohm. Achieving this target signifies that the LIN communication wire is functional and facilitates accurate data transfer. If the resistance exceeds this value, further investigation into the wiring between the battery sensor and PCM becomes essential, indicating a need for repair. This step serves to reevaluate the potential failure area associated with DTC P16E3. Begin by turning the vehicle to off/lock mode and disconnecting the 12-volt battery sensor 2P connector. As before, check for resistance between the connector and body ground to verify if it exceeds 1 mega ohm. A result indicating satisfactory resistance confirms the LIN communication integrity. If the reading falls short, further exploration is mandated to identify the underlying cause of the communication breakdown. Repetition of such checks ensures that all probable sources of errors are scrutinized before concluding the troubleshooting cycle. In this step, you will continue with further checks for potential shorted wires. Initiate the process by jumping the SCS line with the HDS and allowing time to elapse for measurement. From there, check for continuity from the 12-volt battery sensor's 2P connector terminal to body ground, while sequentially disconnecting various connectors to test for disruption in continuity. Should continuity cease when specific components are disconnected, it indicates that the LIN wire is intact, leading to the conclusion that replacement should focus on the open circuit component. This methodical approach allows for isolating issues effectively while ensuring the correct parts are identified for replacement. At this point, you will reconvene your checks focusing again on the 12-volt battery sensor. Reconnect its 2P connector, followed by disconnecting the shutter grille 4P connector for further evaluation. Measure the resistance at specific terminals to establish whether it satisfies the benchmark of 1 MO or higher. If this reading fails to meet expectations, it suggests that the 12-volt battery sensor may be defective, thereby warranting its replacement. This targeted resolution will aid in restoring proper communication once any identified issues are dealt with, ensuring that the battery management system operates as intended. Continuing the process, you will conduct another series of open wire checks focused on the LIN communication integrity. Jump the SCS line with the HDS and disconnect both the 12-volt battery sensor and PCM connectors A50P. This resistance check is designed to ensure that measurements between specified test points reflect 1.0 ohms or less. If this standard is met, it indicates no wiring issues exist between the battery sensor and the PCM. If resistance is above the stated threshold, you must then consider repairs to rectify any observed breaks in the LIN line between these components. In this step, the focus returns to possible failure areas linked to DTC P16E3. First, ensure the vehicle is off and disconnect the 12-volt battery sensor 2P connector. By measuring the resistance at designated test points, you will confirm whether it is 1 MO or greater. If resistance is acceptable, there's a higher likelihood the wiring is intact, which narrows down the root cause significantly. If insufficient resistance is recorded, the potential issues would be connected to the LIN line, requiring further investigation or repairs to establish communication integrity between the battery sensor and the PCM. Continuing with troubleshooting, you will re-engage shorted wire checks. Ensure you've jumped the SCS line with the HDS and checked continuity to body ground after disconnecting the necessary connectors. This process has continuity focused on isolating issues by systematically determining when the connection fails. Once a discrepancy is observed upon disconnecting a specific connector, it signals that the LIN/BAT sensor/LIN wire is functioning correctly, directing attention to the parts needing replacement. This systematic approach is essential for accurately pinpointing electrical faults without premature components replacement. In this penultimate step, ensure the vehicle is turned to the off/lock mode before moving forward. Reconnect the 12-volt battery sensor and disconnect the DC-DC converter connector A3P to make necessary measurements. Assess the resistance between defined points to confirm it is at least 1 megaohm. A failure to meet this standard indicates that the 12-volt battery sensor may need to be replaced or that wiring issues exist. Conducting these targeted checks ensures that when the 12-volt battery sensor is in place, continuity remains at optimal levels for effective communication to the PCM. In the final check for DTC P16E3, conduct a thorough open wire check focusing on the LIN communication paths. Repeat the process of jumping the SCS line with the appropriate technology like the HDS and disconnect the required connectors for resistance evaluation. The measurement taken should align with stipulated standards of 1.0 ohms or less, confirming that the connections between the battery sensor and the PCM remain secure. Should the resistance be found lacking, this indicates a fault that needs addressing for proper LIN communication. Ensuring this last check is complete contributes to both solid diagnostics and effective resolutions for repaired wiring. The 17th step focuses on verifying fuse A24, which plays a role in the overall communication circuit. Turn the vehicle to the off/lock mode before proceeding to inspect whether this fuse is operational. A blown fuse can often contribute to communications failures across multiple sensors, including the battery sensor LIN. If the fuse appears damaged, replace it and resolve any shorts identified in the wiring between the +B horn circuit and the battery sensor. Properly functioning fuses are integral to the safe and efficient operation of vehicle electrical systems, ensuring connectivity across all involved components. During this final phase of troubleshooting, you conduct a crucial open wire check on the +B horn line. Begin by disconnecting the 12-volt battery sensor's 2P connector to obtain accurate voltage readings. Measure the voltage between specified terminals to ensure that it meets expected battery voltage levels. If the measurement confirms the presence of battery voltage, it suggests that the circuit remains intact and communication should function as intended. However, if voltage is lacking, this points to an open circuit needing immediate repair to re-establish proper communication pathways. As you wrap up the troubleshooting for DTC P16E3, conduct the final open wire check specifically targeting LIN communication with the battery sensor. As before, jump the SCS line with HDS and disconnect the necessary connectors, followed by an assessment of resistance between pivotal terminals. A reading of 1.0 ohm or lower signals that the LIN wire between the PCM and battery sensor is intact and functioning correctly. If problems are identified in the reading, direct repairs are required on the LIN wiring to restore communication. This conclusive check is paramount in ensuring that all components function harmoniously within the vehicle's electrical system. Upon completing all the necessary troubleshooting and repairs associated with DTC P16E3, a final verification is required to confirm that the problem has been resolved. Start by assessing the vehicle's overall operation to ensure that it performs effectively without any warning lights indicating recurrent issues. Utilize the Honda Diagnostic System, HDS, to check for any remaining DTCs post-repair, ensuring no new codes have emerged and that previous faults have been cleared. This verification step is crucial to guarantee that the repairs made have effectively resolved the communication problem between the battery sensor and the PCM, ensuring the vehicle can now operate reliably. Preventive maintenance plays a significant role in avoiding recurrence of DTC P16E3 and ensuring the electric components of your Honda CRV remain in optimal condition. Regular inspections of battery connections and electrical wiring can help catch issues before they escalate. It's good practice to routinely monitor the performance of the vehicle's electrical system, watching for signs of irregularities, as these can provide early warnings of bigger problems. Additionally, staying updated with software updates provided by Honda can enhance ECU performance and address known issues that may relate to communication errors. Collectively, these measures contribute to maintaining system integrity and prolonging the vehicle's life. In summary, addressing DTC P16E3 requires thorough troubleshooting steps to pinpoint the source of the PGM-FI-Battery sensor LIN communication error effectively. Understanding the error code, its symptoms, and following logical evaluation pathways is crucial for efficient diagnostics. Accurate identification of communication issues can prevent further complications in vehicle operation, ensuring that the battery system functions properly. Regular maintenance checks and proactive inspections can aid in spotting issues before they lead to significant repairs. By prioritizing these practices, vehicle owners can uphold vehicle reliability, ultimately preserving the Honda CR-V's performance and functionality. Please like and subscribe to the channel. See you next time.